all the participants. Now it is time to start our first keynote by Professor Fred Paas. Let me introduce him briefly. Professor Fred Paas is a professor and chair of research group Educational and Developmental Psychology at the Department of Psychology, Education and Child Study of Erasmus University, Rotterdam, in the Netherlands. He is also a professional fellow at the School of Education, Early Start of University of Wollongong in Australia. He holds a master's degree in human movement science and a Ph.D. degree in instructional technology. His research focuses on the design of effective and efficient learning environment by applying contemporary multidisciplinary scientific knowledge about the human cognitive system. He has published more than 300 articles and book chapters, and he was recognized as one of the world's most productive authors in the 5 best journals in the field of educational psychology. Since 2015, Professor Fred Paas has been the editor-in-chief of the journal Educational Psychology Review, which is the #1 journal in the field of educational psychology. He is also on the editorial board of several other renowned journals, such as the Journal of Educational Psychology, Educational Technology Research and Development, and the International Journal of Environmental Research and Public Health. With this, I invite Professor Fred Paas to deliver his keynote address. Professor Fred Paas.
Okay, thank you very much. Can you all see my screen?
Yes, yes. However, yes, now it is okay.
Okay, fine. Then I will start with my presentation. Thank you for the very nice introduction. And as I said, it's a great honor to be here again and to provide my keynotes and to present you with some new work that we are doing, which is based, of course, on the old work, but it's really a new direction that we are going. And so I'm going to talk about the design of effective learning environments. And I'm going to focus on the old direction, which is instructor-managed cognitive load. And I'm going to contrast this with our new direction, which is focused on learner-managed cognitive load. So first, I'm going to give a short introduction about cognitive load theory. Then I'm going to focus on the strategies that we already have developed since the 1980s, which are all on instructor-managed cognitive load. Then I'm also going to show you that this might actually, by using this instructor-managed cognitive load, we might also have a problem, or maybe even create a problem. And I think we can solve this by introducing learner or self-managed cognitive load. And all this research is not specifically focused on online learning, but it can be applied mostly to online learning because the strategies that we design are rather general. And so they are also most of the times very useful in online learning environments. So first, the field that I'm working in, which is educational psychology, which is, well, you could call it a subfield of the field of education, in which we specifically always focus on the processes that underlie learning. So we try to uncover the processes that underlie learning. And so we look at the interactions between the learning environment and the learner. And well, you can think, of course, one characteristic of the learning environment could be whether it's online or offline, or it could be, which medium, whether you use multimedia or only one medium. And we look at learner characteristics like learner age or the prior knowledge of the learner or the motivation of the learner. And these interact. For instance, you can imagine that, for instance, older learners have more problems of learning in a noisy environment than young learners. So that would be one example. And the interaction between the learning environment and the learner leads to a learning process in which the learner selects, organizes, and integrates information. And this leads to changes. Of course, we hope it leads to changes in our memory. And that's what actually learning is. And we can, of course, determine whether learning has happened by testing people, by looking at tests. And this can be done a retention and performance test. Well, cognitive flow theory specifically focuses on using empirically validated knowledge about our cognitive system or cognitive architecture to optimize the way in which learning materials are presented to learners. So it's about instruction, about the design of instruction in such a way that it matches very well with how we think, how we act, and how our information processing system works. And we focus on complex cognitive tasks because with these tasks, the format of the instruction is really important. Like if you use a badly designed instruction, the learning of complex tasks, then the learning will be very bad. However, if you look at simple tasks, then it doesn't really matter how you design your instruction. Like if you have to learn a list of words, then you can design it in many ways. And even if it's not the best way, people will still learn it. But with complex tasks, the characteristic is that if you do it in a bad way, then people won't learn. So we use a certain model of the human cognitive architecture, which is a very well accepted model, which is used by Alan Baddeley and by even older researchers, but it's still a very often used model in which we distinguish between three elements of the information processing system. And the first is the sensory memory, in which all information from the environment enters our cognitive system. And this memory needs to distinguish between relevant and irrelevant information. And of course, this depends on which task you are working on at a certain moment. So if the information is relevant, it needs to be transferred to our working memory. If it's not relevant, then it needs to be stopped in our sensory memory and not further processed. If the information enters our working memory, then it will be selected, organized, and integrated. And this memory is really important for cognitive flow theory, because this is actually a very limited capacity memory. It is limited in capacity because we can hold no more than 4 to 8 information elements at a certain point of time. And we can also hold it for no longer than 20 seconds. So if we don't do anything with the information that is in working memory for 20 seconds, then the information will be lost. However, if we, for instance, rehearse the information or pay attention to the information, then it can be transferred to our long-term memory, which is actually which has an unlimited capacity. So information that we learn is stored in our long-term memory. And this is done in the form of schemas in which knowledge is related through interconnected nodes of in a network of knowledge. Another important characteristic of working memory is that that there are different processing units. So there is a different processing unit for processing of phonological information, which is called the phonological loop. And we also have one system which is called the visual spatial sketchpad, which deals with visual information. And I will come back to that later, because that's important for the design of instruction, the fact that we have these different systems. So until recently, we implicitly assumed that this our working memory is let's say an limited resource, which means that we can deal with these 4 to 8 information elements, but we can do this anytime and or for a very long time. And so, but recently we started thinking of it more like in terms of a biological system, because all biological systems get exhausted if you work. Like if we use a muscle, then the muscle will get exhausted, and it takes time to recover and to be able to exert the same amount of power. And that's the characteristics of all biological systems, and working memory is also a biological system. So we recently are considering working memory as like a biological system, that if we exert working memory, if we use working memory resources, then the working memory resources will be depleted. So the working memory gets exhausted and needs time to recover. And so we call this the working memory depletion effect. And this effect occurs when cognitive effort on one task depresses performance on a later task due to the first task depleting the resources available to complete the second task. And depleted resources can be restored after rest periods. And we have studied this now in a few studies. One was recently published in Educational Psychology Review, and you can see the title here, in which we try to extend cognitive flow theory by incorporating this idea of working memory resource depletion. And in this study, we compared a strategy of spaced practice to a strategy of massed practice. So it is already known since the late 19th century by Ebbinghaus that space practice, that people learn more from space practice, so practice in which you include some rest periods, than from massed practice, in which you practice all the tasks after each other. So we compared both strategies, and of course the idea was that when we would present students with a working memory capacity task after this practice, we would expect the working memory performance to be lower on the massed practice task, because working memory resources get depleted. So you have less resources left to perform on the working memory task. And that's actually what we found. So this was a kind of, we were able to show that this working memory depletion effect really exists, and working memory cannot be used in an endless amount. So within the theory, we distinguish between two main types of cognitive load, and in which cognitive load can be defined as the load imposed on our cognitive system by the learning task, and by the way in which the learning task is presented to the learners, which we call the instructional design. So first, there is the intrinsic cognitive load, which is the load imposed by the learning task. So the complexity, the intrinsic complexity of the learning task, which is determined by the number of interactive information elements in a learning task. If there are many interactive information elements, then the intrinsic load is high. If there are not many, then the intrinsic load is low. And then we have the load that is imposed by how we present the task to the learners. So, which we call extrinsic cognitive load. And well, this load can, of course, be effective for learning, so add a positive effect to learning. Then we call it germane load, and it can also have a negative effect on learning. And then we call it extraneous load. And I will show you an example. So if you look at this slide, you can see there is a problem formulated in the screen, and which is not easy to read, and which it uses different font types. And there is a very annoying frame around the problem. So we have a problem which is actually rather simple, because it says, suppose yesterday was Tuesday, what day of the week is tomorrow? So this is a problem with a very low intrinsic load, but the extraneous load, so the load imposed by how we present the problem, is really high. So there's a high extraneous cognitive load. And for this problem, it would not matter, because you can present it in this way. You would still be able to solve it and know that the answer is Wednesday. However, if you look at this problem, then it becomes more difficult, because this is a problem which has a high intrinsic cognitive load. There are many interactive information elements. The problem is, suppose 6 days after the day before yesterday is Saturday, what day of the week is tomorrow? So there are many interactive information elements, and you still have this badly designed instructional way of presenting the task. So there is a high intrinsic load and there is a high extraneous load, which might easily lead to an overload of our working memory. And that's why we are probably not able to solve this problem, or less well able than when we present the problem like this. This is the same problem, but presented in without extraneous cognitive load. So this is the same problem, and when you present it in this way, then the intrinsic load is still high, but the extraneous load is low, and so there might be some working memory capacity left to add strategies that can also have a positive effect on learning, the germane cognitive load. We could, for instance, ask the problem solver to think of which strategy they used to solve the problem, which has been shown to be to have a positive effect on learning. So the cognitive load, of course, when we talk about cognitive load, we should also be able to measure cognitive load, and we have been able to measure it, and we do this in several different ways. We use objective measurement techniques and we use subjective measurement techniques. So objective measurement techniques are based, for instance, on primary and secondary task performance. Well, primary task performance is not really a reliable measure, because then we would, for instance, say if students work longer on one task than the other, then the cognitive load is higher. But that's, of course, not a really good measure. But secondary task measures are used very often, and this means that the performance on a secondary task, a simple task mostly, is used as an indicator of the load imposed by the primary task. So, for instance, in this example that I show, students had to learn from an encyclopedia text, and at certain points in time, the letter that is presented at the opposite side of the screen changed from color. And when it changed in color, they needed to respond as quickly as possible by pushing a reaction time button. And so you can imagine that if the primary task is really difficult, the reaction times will be rather slow, because you have to focus all your capacity on the primary task. However, when the primary task is simple, then you have a lot of capacity that you can use, and the reaction times on the secondary task will be fast. So by using this technique, the performance on the secondary task can be used as an indicator of the primary task, the load imposed by the primary task. We also have used psychophysiological techniques, and for instance, we have used heart rate variability. We have used eye movements, which can say something about where people look, how long they look, for the differences, the scan path that people have on a certain instructional materials. And this can tell us something about the load they have to spend on the task. We also have looked at pupil dilation, and this also seems to be a rather sensitive measure of working memory load, but especially for young people. For older people, it is not really a sensitive measure. Then we also use subjective measure techniques, and actually these are the techniques that we most often use because they are really easy, and they are based on the assumption that students or learners are able to introspect on their cognitive processes or on the amount of effort they have invested. So we just asked the students, how much mental effort did you invest? And they can answer this on a Likert scale. To measure cognitive load, we mostly use two questions when we want to measure overall cognitive load. This is how much mental effort did you invest in the problem, and how difficult did you think the problem was. There are also scales in which we with which we can measure the different types of cognitive load: intrinsic load, extraneous load, and germane cognitive load. These rating scales are a bit more complex because they contain more questions, and these can be used when you are interested in the different types of cognitive load. Well, here I present an overview of all the techniques that have been developed since the first one was in 1982 by John Sweller, which is the goal-free effect. And you can see here there are 17 techniques that were developed, I think here until 2012. This is presented in a recent review article, which we have published in Educational Psychology Review about cognitive architecture and instructional design. And then 20 years later, because we did already publish the first article with the same title in 1998. So if you want to know something about cognitive load theory, about the different techniques, then if you read this article, then you know, I can say you know everything. So all the techniques so far have mostly been focused on instructor-managed cognitive load, which means that we provide guidelines for instructional designers or teachers, how they can design the instructional materials effectively so that the learner performance will be high. And I will discuss shortly 5 effects that we have found, which are also, I think, the most studied effects so far. But these will give you an indication about the instructor-managed cognitive load. So the goal-free effect is actually the first effect that was found. And this was found in problem-solving domains. So for instance, if learners have to learn physics or math, then they have to solve, they have to learn to solve problems. And the idea is then the conventional idea that you have to practice solving a lot of problems. And so what John Sweller showed was that the type of problems that is used typically in which you have given the problem, you have some operators and you have a specific goal. In this example, for instance, you have to calculate how far a car has traveled. And to solve these problems, students have to apply a so-called means-ends analysis, and in which they find the formula for calculating distance, and then they will find out that they cannot solve the whole equation. So there is a sub-goal, they find the formula for that, and there is a new sub-goal, and so on, until the problem is solved. So all these sub-goals need to be held in working memory. So it imposes a very high load on our working memory. And whereas this strategy leads the learners to solving the problems, so they will be successfully in solving the problems, they don't learn about the problem, because the solving process imposes such a high load on the working memory that there is no capacity left to learn about the underlying structure of the problem, which is necessary to be able to solve similar or new problems. Well, one idea to prevent students from using this very demanding strategy is by getting rid of the very specific goal. Like, you don't ask students to calculate the distance, but you can ask them to calculate the value of as many variables as possible. And so when you have this less specific goals, then students use a different strategy. They will use a strategy in which they search for an equation with only one unknown, and they repeat this process. And this is actually not imposing a high cognitive load and enables students also to learn about the underlying structure of the problems. So the results of this study is comparing both strategies, goal-specific or goal-free, show that students learn more with goal-free problems, so they are better able to solve similar problems, but specifically they are better able to solve new problems. One other way we have found, which is actually is based on the same effect, that solving a problem by using this goal-specific means ends analysis is not effective, is the so-called worked example effect. So instead of using a goal-free problem, you can also present the learners with the problem and the worked out solution and ask them to study the solution instead of solving the problem. And also with this strategy, the students learn much more than when you ask them to solve problems. So studying worked out examples leads to better learning than solving problems. And this is also another strategy which is also again based on this worked example effect. This is so-called completion effect, in which we present students with partly worked out problems. So problems with a worked out solution, they're asked to study the solution, but also to fill in certain aspects of the solution. And of course, you can, in the end, you want students to be able to solve the problem. So during the instruction, you will increase the number of things the students needs to complete. Well, one type of instruction that we often see in online, but also in offline learning materials is instructional materials in which we have to learn from a picture and a text. And the text and the picture refer to each other, and you can only understand the learning materials when you integrate both the text with the picture and the picture with the text. And you cannot understand the picture without understanding the text, and the other way around. But in this case, it's really difficult. Well, it's actually impossible for human beings to focus on the text and the picture at the same time. So therefore, we create a so-called split attention effect. So if you look at the text, if you read the text, then you need to keep elements from the picture in your working memory. And also, if you look at the picture, you need to keep elements from the text in your working memory. And this creates a very high cognitive load and has a negative effect on learning. So one way to solve the split attention effect is by integrating the information into the picture, so that students do not have to split their attention as much as in the conventional materials. Here, one example is shown, which looks actually rather messy, but it leads to much better learning performance than the instruction which is presented on the left side of the screen. One other way to solve this split attention problem is by using our knowledge about the separate processors in our working memory for the visual information and for spatial information. So we can present the text by audio or use spoken text. And then the picture, of course, we need to look at. But the point is that we as human beings are able to look at the picture and listen at the spoken text at the same time. So in this case, the integration process of the information is much easier. So these techniques and also these 17 other techniques, the other techniques that we have found are all based on on instructor-managed cognitive load. So we can say that cognitive load theory has given us a comprehensive collection of techniques that, when employed by instructional designers, can lead to increased learner performance by substituting productive cognitive load for unproductive cognitive load, which means that we try to get rid of the extraneous cognitive load and impose more germane or intrinsic cognitive load. So, but this also creates a problem, we think, because we think that learners are exposed to an education system of consistent, well-structured learning materials designed based on these cognitive load theory principles, have the problem that they may be poorly equipped to deal with non-CLT compliant materials. Because learners are, especially through the internet, they are more often confronted with badly designed learning materials than with cognitive load compliant learning materials. So if you are only used to work with the well-designed learning materials, then you might really have a problem if you have to deal with problems that are not designed with cognitive load theory in mind. And so this led us to the idea to think of a potential solution, which is that we might also be able to teach learners how to apply the cognitive load theory principles themselves to manage their own cognitive load, so that they will be better equipped to deal with non-CLT compliant materials. So the idea is that we might be able to teach students to apply cognitive load theory themselves and to regulate their own cognitive load, to design maybe their own learning materials. And we have conducted several studies on this issue. Well, only a few studies yet. I think these are the only ones until now. But in these studies, for instance, in the first study that is mentioned, the students were told about cognitive load theory, and they were instructed that they with split attention problems, they can circle the relevant information, they can number elements, and they can highlight keywords to reduce their cognitive load and focus more resources on the relevant information. In another study, students were, which was with online materials, the students were able to physically move digital text objects to associated parts of the diagram. So you can imagine that if you have a split attention problem with text and picture, then you might be able to integrate yourself the text into the picture if you can drag and drop the text to the relevant places in the picture, and then you have a better designed instructional material. In another study, all students were also instructed to highlight or draw arrows between the textual and the pictorial information. And in a study by De Koning and colleagues, the students were able to physically or mentally move text segments to associated elements in a picture. And this is actually interesting because so in this study, students were also confronted with split attention examples. And in one condition, the students were instructed to mentally move, so to imagine that they move the relevant text segments to the elements in the picture. And this also had a positive effect on learning and was better than learning from split attention examples. And one other aspect that we recently studied was to use finger pointing, like using your hands when you have to deal with information that is in split attention examples. And the interesting thing of these self-management studies is the design of the experiments, and which I show here, which actually consists of two phases. There is a guided phase. So we normally compare three groups. And in this case, we have used split attention examples. So one group received conventional split attention instruction, which is the bad instruction. Then there is one group who receives integrated instruction, which is the instructor-managed, good instruction. And there is a group which received split attention instruction, so the bad instruction, but this group is told how to deal with this. So they are learned the strategy to deal with the split attention problems. So after this instruction phase, after this guided phase, they receive a test, and then we would expect that the conventional instruction would do really bad, because that's what we have shown again and again. The integrated condition would do very good, because there we have solved the split attention problem with instructor-managed cognitive load. And then we have the learner-managed cognitive load, and we would also expect them to do better than the conventional split attention condition, because they have learned to deal with the split attention problem. And then the interesting thing is the second part of the experiment, in which all students are confronted with a new task, a totally new problem, and but this problem is badly designed. So it's a split attention problem for all students. So the students who worked with previously with the split attention problem receive a split attention problem again. The ones who worked with the CLT-based design now also receive a conventional split attention example. And also the self-managed group also receives a conventional split attention instruction. Well, the conventional group will do bad again, because they have not learned to deal with it, and they have to deal with the split attention problem again. The second group, the integrated instruction, was previously has worked on a very well designed example, and now has to deal with this badly designed example. And so we expect them to do very bad. And the last group, which is then the self-management group, well, they have learned how to deal with split attention problems. So we expect them to be able to apply these strategies that they have learned to learn from the example. And their learning performance would actually is hypothesized to be highest. And that's what we found in these studies, and which this is actually, so this is a new direction of the theory, and this is actually very interesting, I think. One example of these studies is mentioned here. This is a recent study in which we learned students, or explicitly instructed them to use finger pointing on split attention examples to connect the information, the associated information. So there was this split attention condition. Text, the picture was separated. Then we had the integrated format, which is the good format, in which the text is integrated into the picture. And then we had the split attention format, and we taught students to use their fingers to connect text with the picture. So after that, I received the test, and then in the second part of the study, which is the unguided, all students received a split attention problem, and they, of course, had to learn with it. And what we found, of course, was what I just told you, that this group who was taught to deal with the split attention format performed highest. So there are other potential self-management effects. We haven't studied them, but there are some interesting, of course, with let me say, instructional guidelines that we could present to learners so that they themselves are able to deal with split attention effects. And one of them is the modality effect, which I showed you earlier on. If they are confronted with a split attention format in which there is a text and a picture, then we could tell them that they can use maybe a function on the computer to have the text read, so use spoken text instead of written text. Because we are able to listen to text and look at the picture at the same time, but we are not able to look at the text and look at the picture at the same time. We also have the so-called collective working memory effect. So we could instruct students to, when they have to learn simple tasks, they should do this individually. But if they have to work on a complex tasks, then they should try to work with other students. We have previously shown in our studies that the collaborative learning is only effective when the tasks are complex, and so complex that an individual is not able to solve the task or learn the task. However, if a task is not complex, then collaborative learning is actually worse than individual learning. And you can imagine why, because if you collaborate and you have to, you have to divide roles and you have to create common ground. So this all uses your cognitive resources, but if you have a simple problem, that's not really necessary, and it actually imposes an extraneous cognitive load. Other studies point at an effect that we, for instance, if we have to make a test, which is like a high stakes test, then people get anxious, and some students get very anxious, and they have worries, intrusive worries in their working memory, and these worries use working memory capacity. So in the study, which was done by Ramirez and colleagues, they told students to write down their worries just a few minutes before the test. So, and they showed that this offloading of the worries from working memory onto the paper had a positive effect on their test performance. So one instruction to self-managed cognitive load could be to write down your testing worries shortly before a test, because this can be used to offload these worries from your working memory, and you can use this capacity then to perform on a test. Another aspect that is a more general strategy is that you could instruct, and this is mainly suitable for children, to avert the gaze or close your eyes when you have to learn or listen to complex information. This is something that when we, at an age of 12 and older, we do this automatically. If we have to work on a complex problem, then we will avert our gaze or look into the air, and we won't look into the eyes of someone, because that also imposes a load. So, but we do this automatically. So this is an evolutionary strategy, but children are not able to do that, and they could be, research has shown that if they are instructed to do this explicitly, then this will lead to higher performance. Another strategy is related to like the rest periods that I talked about. I talked about working memory depletion, and so we could instruct students to walk in nature or watch nature pictures after you have worked on a complex task and before you start working on the next task. And there are actually studies, well-controlled studies, that have shown that actually walking in nature, but also watching nature pictures, has a restorative effects on your attention, but also on working memory. So we recently did a study in which we had students work on a working memory task, on several tasks, and then they either looked at natural pictures or urban pictures, and the idea is that natural pictures will replete your resources and urban pictures will actually not replete, they will further deplete your resources. And so what we found later on a working memory test was that the group that watched the natural pictures had a much higher working memory capacity outcome than the group that watched the urban pictures after working memory depletion. Well, one final effect, which is actually often used, of course, but which could be specifically instructed and also specifically added to when we have to learn from animations, it would of course be good to present control buttons with the animation and to instruct students to stop or rewind, or maybe could also be forward the animation or maybe the video in such a way that the working memory resources are aligned with the speed in which the animation is presented and in which you think you have learned. So this is my final slide in which I have also presented some final strategies that we have already studied, but only as instructor control strategies. So for instance, we can instruct students to trace the learning elements, like we did, for instance, with learning Chinese characters or learning from geometry, which you see here. So what we show is that if you trace the elements, then you learn more from the information than if you don't trace the elements. And also, if you point at the information elements or use your fingers, for instance, in finger counting, then this has a positive effect on learning. So for some strategies, we use them automatically, but like this tracing is not really something that we would normally do in learning materials, especially not if it's, for instance, about geometry and things like that. But this has a positive effect, and so it could be instructed and used as a self-management strategy. And there are several reasons for this effect that we have found, or that we have generated. So on one side, using your finger together with your cognitive system, that leads to schema enrichment. So taking action in response to information, in addition to simply seeing or hearing it, creates a richer memory trace. So which might make the recall of the information later on easier. There's also, or there can also be a reduction of working memory load, which might be clear when you look, for instance, at finger counting. Of course, your fingers, they also create a kind of memory, because you use it to offload information from your working memory onto your hand, and that's also what what happens with pointing when you deal with learning materials. There is also an evolutionary explanation, because we have in the theory we also use an evolutionary account, and we think that human movement is biologically primary knowledge for which working memory limitations may not be critical. So the movements that we make actually don't impose a load on our working memory, but they can be used to support the learning from what we call secondary knowledge, like geometry or learning letters or characters. Finally, there is a lot of research showing that human beings, the attention is automatically directed to the space around the finger or the hand. So the hand or the finger is a cue that automatically and without effort leads our attentional system to the space around the hand. So it can be used as a kind of cue. So these were all strategies that are currently also studied, and in which we have more or less replaced our focus from instructor-managed cognitive load to learner-managed cognitive load. And so I think it's for learners, of course, it is very good if they learn also to deal with instructional materials in the most efficient way, and are not only presented with instructional materials that are very well designed, but are also able to deal with materials that are not well designed, because in practice they are confronted with these materials very often. So this was my presentation. I hope that it was interesting for you. And of course, I'm happy to answer questions if you have them.
Thank you, Professor Fred Paas, for your insightful talk on cognitive psychology and self-management on different aspects of attention, working memory. We use all these terms. We use all these terms for our machine learning and artificial intelligence for say artificial and machine, but you have worked everything on the human being and on the self-management. Really, it is a very insightful talk. So those say computer area researchers who are working, they should know more about what is happening in the human brain, what is happening in the working memory of the human. Then only they can model the machine in a proper way. So thanks for the excellent talk on all your research. Last year also we have listened to one area of your research, this time on self-management, attention, and many new areas you have added, and very beautifully you have lucidly you have explained your research. Thank you for the nice talk.
Thank you.